Good afternoon, dear students.
Good afternoon,
Today,
sir.
yeah, I think only 11 students are present. Uh, 12. Okay. So in the last class, we have solved few problems on the undamped free vibration of a single degree freedom system. Till now, we are just observing the motion which is happening for a spring mass system only. For a spring mass system, the vibration or the oscillation, it is taking place uh, in most of the cases in the longitudinal direction. Okay, so today we will see the oscillation of a simple pendulum. So as we know, the oscillation of the simple pendulum results into the vibration, and that is the phenomenon by which we can describe the vibration very easily. So in one lecture, I told you how to analyze the vibration or how to understand the concept of vibration by the use of or by taking the example of simple pendulum. So today we are going to see how to find out the natural frequency of a simple pendulum, just like the natural frequency of spring mass system. So when we categorize the vibration by looking at the type of motion, so you can categorize it into three categories. So one was longitudinal vibration, for example your spring mass system. Second one is your translational vibration. Second one is the this one torsional vibration. So in torsional vibration, what was there? So one disc. Okay, so disc was fitted with the help of what shaft, isn't it? So a disc was fitted, and this is fitted, and a disc is rotated. The shaft, it also gets rotated with respect to its axis. So there will be one twisting and untwisting movement. So by that oscillation also, so we will get torsional vibration. Then another is the kind of your transverse vibration. So in transverse vibration, the mass will move perpendicular to the axis. Okay, so in pendulum what happens? So from mean position, it's if its reference axis, if it is rotating, okay, if you imagine that if its length, okay, if its length it is deflecting, okay, so with respect to this length, where you will get the velocity in the tangential direction, isn't it? So the motion is happening in the tangential direction of the axis, okay, or tangential direction of the length of the pendulum. So this type of motion or these type of vibrations are called as transverse vibration. So today we are going to analyze this transverse vibration for the simple pendulum. Okay. So the next one was the torsional vibration. So we will analyze that torsional vibration after this simple pendulum. Okay. So here, though there are some overlappings are there, just you I will tell you actually what these terms are. Okay, some corrections I have done actually. That is why some overlappings you will see. Okay, so ignore those things. Just we will concentrate on the concept. So if you just understand the concept, then you will be able to solve problems also as well as this analysis. Okay, so here in short cut I have written that natural frequency of simple pendulum. So all of you know that simple pendulum, it oscillates. If you give some angular deflection, it oscillates with respect to this mean position or the equilibrium position. Okay, so what is the difference between the translational motion and this transverse motion. So in translational motion, what was happening? So when the spring was connected with the mass, so the mass was moving up and down, isn't it? And the deflection or the displacement was given as linear displacement. That is why it is called as translational vibration. Okay, so we can give displacement x in the downward direction or upward direction for translational, but here it is transverse oscillation. Okay, so you can see we need to give some angular deflection, okay, or angular displacement to the bob, okay, or to the simple pendulum. This is a string and this is the mass, metallic mass or whatever it is, okay, wooden mass. So this is the pendulum. Okay, so here the difference is that here the displacement it is happening in angular direction. Understood? So the same thing, this bob is hanging from a fixed end. The point where it is pivoted, it is O. Okay, it is denoted by O. This is the mean line. This is the mean line or equilibrium line. So you can denote it by writing equilibrium line. So the initial position of this bob is this one. Okay, so here the string will be there. This is the length of the string. L is the length of the string. Small l is the length of the string, and small m is the mass of the bob. So here I have not written all those things, just in shortcut I have written. So when you will derive, so you need to write all these things, that one bob of mass m, it is hanging from a fixed end where it is pivoted at point O. The length of the pendulum will be L, and an initial displacement theta is given to the pendulum. So it is arrow mark is given at the head. So one theta displacement it is given. So what is this? This is free vibration. Okay, and this is single degree freedom system because only one mass is attached here. Okay, and motion is happening only in this direction. That is why this is single degree freedom system. So to find out degree of freedom, so we will concentrate on the motion, number of motion. Okay, so when this theta is given, so earlier in the case of spring mass system, x was given, but it was longitudinal, but here it is angular. So you need to see that thing, okay, angular. So for this body, displaced body, let's say this is position 2. It is 1, the mean position is 1, here it is 2. So at position 2, okay, or at the displaced position, so we need to resolve the forces. We need to see the forces which are acting. Okay. So how to find out the forces? So one mg force will act downward. This will be the weight of the mass, or this is the weight of the bob. So as because there is angular deflection, so the bob will be having two components of his weight, isn't it? So one along the direction of the string, which will be in opposite direction because in the downward direction the weight is acting. Okay, so this will be your cos component, cos theta, mg cos theta, and this will be your sine component. Okay, this is the tangential direction of motion, and because a tangential direction of the force, and because of this force the motion is happening. Okay, mg sine theta, and this mg cos theta is equals to the tension of the string. Okay, this is not torque, this is tension, this is tension. So you need to write the tension in the string is T. This will be balanced by mg cos theta. So why you can say that this is balanced? Because the bob is in its position, it is not going out. Okay, by by destroying the string. Okay, so it is in its position, that is why there is no movement in this direction. So T will be equals to mg cos theta. So here T is the tension in the string, so the motion is only happening because of this force mg sine theta. Okay, so this is the external force. Understood? So if you want to apply Newton's second law of motion, so for this bob, so you need to write the force component as moment component, isn't it? Because what Newton's second law of motion actually says for angular displaced body, that the external moments acting on the body will be equals to I theta double dot. So what is I? Earlier I wrote actually IP. So but please you write I, because IP is polar moment of inertia. That is a different thing. So you also know that thing in strength of material you have studied. So only I you need to write, capital I. So this is moment of inertia, okay, of this bob with respect to point O. Okay, so I theta double dot will be equals to mg sine theta. Mg sine theta, this is force, but you need to take moment because I theta double dot is moment, isn't it? So mg sine theta into L. So mg sine theta, this is force, and this is the distance. So you will get the moment mg sine theta into L. Force into display, this distance or displacement will give you the moment with respect to point O, and this will be equals to what? I theta double dot. But when you will be considering mg sine theta, so you need to give one negative sign. So why this negative sign is applied? Because in earlier case, in translational motion of the spring mass system, so whatever motion it was happening in the downward direction, those were positive, and whatever motion or whatever parameters you were taking on the upside of the mean position, those were negative. Okay, so here also you can see the theta, if theta direction is positive, this mg sine theta direction is negative, isn't it? Because this is directed towards the mean position. Okay, and for this only the bob will move in the opposite direction. Okay, means the bob will try to regain its minimum energy. Okay, that is why it will try to move in this direction because of this component of force. And what will be the total moment, then mg sin theta into L, and direction will be negative to that of I theta double dot. And I is what? I is the moment of inertia. Theta is what? Theta is the angular deflection or angular displacement. Theta double dot is the angular acceleration. Okay, angular acceleration. Earlier it was mx double dot, now it is I theta double dot. Means in angular deflection, you need to write the NSL, Newton second law of motion equation, in the form I theta double dot. Understood? So earlier it was mx double dot, now it is I theta double dot. So in any problem where you will be getting any simple pendulum, so when we will be writing the Newton second law of motion, then equation, then we need to write I theta double dot or angular deflection. Understood? So I theta double dot will be equals to the external moment. So external moment will be only formed by this component mg sin theta component, because mg cos theta and t, it is balanced just like the static deflection. Okay, so here it is balanced, mg sin theta L. Okay, so mg sin theta into L will be the only moment, so which will be acting in the negative direction. Okay, means in the opposite direction, so minus sign is applied. So now if you just rearrange, so I theta double dot plus, because if you just uh, place it in the left side, then positive, it will be positive. So plus mg sin theta into L will be equals to 0. Now you can rearrange. So I theta double dot, don't write ip theta. So I theta double dot plus mgl. Okay, mgl sin theta will be equals to 0. This sin theta is what? So sine curve, all of you know, sin theta, it is a non-linear term actually. Okay, so that is why, so for this displacement is what? Very small. This angular displacement is very small, 4 degree 3 degree displacement. Okay, so for small angles, so when theta is almost approximately 0, so sin theta will be how much? So it will be equals to 0. Means when theta tends to 0, so sin theta is also tends to 0, isn't it? So put it 0. If theta is 0, then sine of 0 will be what? 0. Means theta will be 0, then sin theta is also 0. Okay, so no need to write this term. Understood? Oh, sorry. Yeah, so yeah, when theta is small, because when theta is 0, sin theta will be also 0. That means what? So instead of this theta, what I can write? Yes, that same concept, that sin theta, instead of sin theta, this theta I can write, isn't it? Because for this one, theta small, sin theta will be equals to theta. If you consider theta will be equals to 0, then sine of 0 will be also equal to 0. Means theta will be equal to sin theta. So instead of sin theta, I am writing here theta. So again rearranging, so you will get I theta double dot plus mgl theta. Instead of this theta, I am writing here theta equals to 0. Now this equation is linear equation. Okay, so earlier this equation was non-linear equation. Understood? So theta double dot, so mgl by I, so mgl by I, theta equals to 0. Okay, so what is mgl by I? So mgl by I have taken as omega n square. So earlier, so it was k by m, now it is mgl by I. So omega n square, here you need to write that we have taken omega n square equals to mgl by I. So what is omega n? Omega n is the natural frequency of the simple pendulum, because for every system there is a natural frequency. Now I will just calculate the value of omega n. So here it is same mgl, and for this I means for this bob which is having mass m and length l, the moment of inertia with respect to this axis, mass moment of inertia with respect to this point will be with respect to this point means with respect to the axis which is vertical, okay, and which is going through this point O. So with respect to this point is ml square, okay. So L is, you can treat is like radius of gyration, so it will be ml square, okay. So L is basically the length of the pendulum. So mgl by ml square. So what you will get, z by l. So if you strike it out, so z by l will be there, because l square. So only l will left. So z by l. So I have written that I equals to ml square, mass moment of inertia about O. Understood? So this is the value. So after you uh, just do the calculation, so you will get omega n will be equals to under root z by l, because omega n square is equals to z by l. Now you are getting omega n equals to under root z by l radian per second. So earlier for translational motion, omega n was how much? How much? K by m. Under root k by m was the natural frequency. Now for this displaced body, so omega n will be equals to under root z by l, and its unit is radian per second. So if you have got omega n, then you can find out small f, natural frequency, linear natural frequency. This is angular frequency, this is linear frequency. F is equals to 1 upon 2 pi under root z by l hertz. Understood? So from this equation, so you can write this equation, okay. So this is the equation of motion, for this simple pendulum, and this is the expression for natural frequency, and this is the expression for linear frequency. I told you that for every system, so we are going to find out the natural frequency as well as the linear frequency. Understood? So again we will see what are the things actually. See, this is the bob when it is displaced by giving an angular deflection theta. So this is the position. So here two forces, weight forces will act in this direction, theta direction, mg cos theta, and here this is sine component, mg sin theta. These are the forces. This mg cos theta and this tension of the string is balanced, okay. So only due to mg sin theta the motion will happen, okay. So at the displaced condition, so what, how does actually parameters are changing? So this is theta in this direction, this is positive, okay, and this is I theta double dot, because the direction of theta is this one, so I theta double dot will be this one. So this is inertia, for inertia moment, I theta double dot. Then the restoring torque, okay, or restoring moment will act in the opposite direction. This torque will what, try to regain, okay, or try to regain the original position of the body, okay. This moment will try to regain the original position of the body. That is why it is directed in the opposite direction. So its value is how much? mgl sin theta, and this is the external what, moment, okay, or external torque you can say. This is the external moment. So according to Newton's second law of motion, external moment but in the negative direction will be equals to I theta double dot, and from this only you will get the equation of motion, and finally you will get the natural frequency of simple pendulum and linear frequency of simple pendulum. Understood? So now I think your this one point is clear. Now your natural, now you will be able to find out the natural frequency for simple pendulum also. So if you are having any doubt, so you can ask, okay, or you can ask in the comment section also. Anyone? Yeah. Any doubt? Okay. So now let's, yeah, so you can see another example here. This is actually one problem, okay. So what is there actually? So this is one small bar or rod. The problem is not written, just I think this problem actually it was a gate problem or IAS problem, so I solved that. That is why it is there. So this is actually yeah, one small pendulum. Okay, you can say this is also a pendulum, but here small bar or rod. Okay, small bar or rod is there, but here the mass, one mass, it is just hanging. Okay, so with attached, which is attached to this bar, okay, or rod or small shaft, you can say. Okay, so the it is also axial vibration. Okay, axial vibration. So this is not a pendulum. Please just note it down that this is not a pendulum. So axial vibration will happen just like your spring mass system. Okay, so how this axial vibration will happen? So when you will apply some force, okay, so P, so P is the force, external force. So here you need to find out uh, the what natural frequency as well as the linear frequency. So for this type of system, so what is delta actually? If length of this system is L, if area of cross section is A, is if modulus of elasticity is E, because P is given, load is given. Okay, so you can find out what you can find out. You can find out the total deflection delta. So delta is how much? PL upon A. So in strength of material, so you have studied this thing, that when tensile force is acting, because this is tensile force, okay, outward force, it is acting on a system. So the deflection, if it is denoted by delta, so it will be how much? So PL upon A, isn't it? So now you can find out the stiffness K. Okay, so K of the bar, isn't it? So K is what? K is what? So K, spring force is what? P equals to K delta, isn't it? So K will be P by delta. So total force will be equals to the spring stiffness will be equals to total force by delta, isn't it? Because P is equals to K delta or Kx, spring force equals to Kx. So instead of X, we will be writing delta. Okay, so to find out the spring constant, so we will be writing this way, P by delta. So P is what? Or delta is what? P will be remain as P. So delta is what? PL by A. If you put PL by A, so you will get A upon L. Understood? So now your mass is given. This rod is massless. The mass is M. So omega n is what? So in translational motion, so omega n is given by under root the mass, under root the stiffness divided by mass, means equivalent stiffness divided by mass. If there are two springs or two rods, so it will be equivalent stiffness. So generally it is K by M. Okay, so this is the basic formula for translational motion to find out the natural frequency. So what is K? So K is A upon L. Okay, and M will be remain as it is. So this is the natural frequency, which unit is radian per second. I think you will be able to find out for this type of system what will be the natural frequency. So these are the general expression, actually general terminology which are used. Some values may be given, so you should know all these formulas. Delta equals to PL by AE. So then you can find out a natural frequency also. Small f will be equals to what? 1 upon 2 pi. Okay, because capital T is what? 2 pi by omega n. So f will be what? 1 upon so T. Okay, so whatever value you will get for time period, so inverse of that will be your linear frequency. So 2 pi upon 1 upon 2 pi under root A by Ln. So each unit will be hertz. Understood? So this way you need to solve some of the problems of this kind. Okay, the simple pendulum and this type of translational system. I think this concept is clear to you now. Okay, so in the next class, so we will see the deflection or the equation of motion for torsional vibration. Okay, so one shaft will be there, one rotating disc will be there, so there will be twisting and untwisting movement. So for that we will be solving one problem also, and this thing we will do it tomorrow. Okay, because one class is still actually I didn't take that class, so I told you that I will take that class on your lab period, but due to some problem I could not take that class, but I will take that extra class. Okay, and up to this much, means up to this torsional vibration, so your syllabus will be there for your class test. Understood? Okay, dear students, if you have any doubt, so you can post your doubt, or if you don't have any doubt, then you can leave the meeting. Okay, so thank you, dear students, for listening.
Thank you, sir.
Yeah. Yes.
Thank you, sir.
Okay.